This video will discuss solving problems at the level that they would be presented in general chemistry using the Clausius-Clapeyron equation. So we're going to talk about the different forms of the equation that we see in a general chemistry class, how we work problems using those forms, and I'm going to point out some of the mathematical difficulties some students have using those. Now, because there was so much writing in putting together this video, I pre-wrote most of the equations, but I still think that the best way to use this video is to follow along the logic, work the problems yourself along with the video so that you can get, a feel for the flow of the problems and the logic of the math. So, first I'd like to acknowledge Pearson Education. I am using some images from the lecture PowerPoints for the TRO, Chemistry and Molecular Science text, the text that we use in our class. So the images are copyright from Pearson Education from that book. Okay, just to remind ourselves, the Clausius-Clapeyron equation relates the vapor pressure and temperature, and it lets us make predictions between the two, right? And so just to remind ourselves, when a liquid is at a given temperature, right, there's an average kinetic energy, but there are molecules in the liquid that have a greater kinetic energy than that, and molecules that have a lower kinetic energy than that. And there are some molecules, some fraction of those molecules, that have enough kinetic energy to break the intermolecular forces holding those molecules in the liquid phase. Those can enter the gas phase, and so then that is our process of evaporation. And once they enter the gas phase molecules exert a pressure. That pressure is the vapor pressure. Okay? And if we raise the temperature, then the average temperature of the liquid, or the average kinetic energy of the molecules in the liquid, goes up. Now, a greater fraction of those molecules have enough energy to overcome the intermolecular forces. Right? So more molecules can escape. So in general, at a higher temperature, we get a greater vapor pressure. Okay? So that's what we're looking at with the relationship between temperature and vapor pressure. So if we plot that, we see that for this variety of liquids, that trend holds true, right? As temperature increases, the vapor pressure increases in a nonlinear relationship, right? And we can see that for different liquids, the vapor pressure is different at different temperatures. So, for example, right here, diethyl ether has weaker dipole interactions, right? If we look at ethyl alcohol, it can hydrogen bond, but it can only donate one. If we look at water, it can hydrogen bond, but it can both donate and accept two. And if we look at ethylene glycol, it can hydrogen bond even more strongly. So we see that the stronger the intermolecular forces, the lower the vapor pressure at a given temperature. Okay, so we can see that the vapor pressure is related to the strength of the available intermolecular forces. So we're going to focus on this diethyl ether curve, right? So it ends up, right, whenever we have a curve plot, we like to find if there's some linear relationship we can find, because that makes it easier to deal with graphically. And so we found that if you plot 1 over the temperature in Kelvin on the x-axis and the natural log of the pressure on the y-axis, you get a straight line. And after studying this straight line, people found that the slope has a very specific relationship, right? That the slope of this line is equal to the negative, because it's a downward slope, of the heat of vaporization of the liquid divided by the gas constant R in energy terms, right? Where R is equal to 8.314 joules per mole Kelvin, right? That's a number that we will need. We'll come back to this plot in just a second. Let's look at the equation that comes out of this, right? So if you look at the theoretical form of the Clausius-Clapeyron equation, you get this exponential equation. This is the way our book presents it. It is that the vapor pressure is equal to some proportionality constant beta times an exponential term, which is negative heat of vaporization divided by the gas constant R times the temperature. Now, this is a way to express this, but I'm sort of old school mathematically. So rather than use this exponential term, I like to use the natural base E. So using the natural base E, we get that vapor pressure is equal to the proportionality constant beta times E raised to this power, negative heat of vaporization divided by the gas constant R times the temperature in Kelvin. Okay? So what we're really interested in, we said, is the relationship between vapor pressure and temperature. Well, it's always difficult when something that you're interested in as a variable exists in an exponent. So one of the things we can do is get that out of the exponent by taking the log. And so since we're using the natural base E, it makes sense to use natural logs. So if we take the natural log of the vapor pressure, the left side of our equation, then we take the natural log of the whole right side of the equation, right? But one of the log rules we remember is if we take the natural log of A times B, that's going to be equal to the natural log of A plus the natural log of B. And so, since we've got two terms here, right? We've got beta, a proportionality constant that is related to the identity of the liquid we're talking about. And then we've got this term multiplied by each other. That becomes the natural log of beta. Right? Be consistent. Right? It's going to be the natural log of beta times the natural log of this whole exponential term. Right? Now, there's another log rule then that we have to remember. Right? That is, if you've got the natural log of E raised to some power, the natural log of that is just the power. So since this is our power, it becomes the natural log of that whole term. And so the power moves down into something we can evaluate algebraically. Okay? And if I have this term and this term, then I can just, since they're added together, it's the same, we can put the second term first and the first term second, right? So, if we've got our natural log of our vapor pressure, so now we can sum that up. Our natural log of our vapor pressure is on the left side, right? That negative heat of vaporization over R we can pull forward and make 1 over T. We can pull 1 over T out of that term, multiply those together, and then we have the natural log of beta. And what's nice about this is that we've created out of this a linear expression where the natural log of the vapor pressure is the y variable, 1 over the temperature is the x variable. This whole fraction here becomes the slope, and the natural log of that beta term becomes the y-intercept. And so we've taken this nonlinear exponential equation and turned it into a linear equation that's easier to evaluate graphically. So one thing we can do with the Clausius-Clapeyron equation is evaluate those plots that we saw. So let's look again at that plot of the vapor pressures of the vapor pressure versus temperature plotted as a Clausius-Clapeyron plot for diethyl ether. Right? So this is where I already wrote this in, but I still think we should follow along here. Right? So if we start off, right, we had the slope, which is negative 3,478 in units of Kelvin, right? Since we've got the rise has no units, right? The change in the y variable, since it's a natural log number, it has no units, right? So our numerator has no units. Our run, the change in the x variable, is in units of 1 over Kelvin. And so if we assess the units, 1 divided by 1 over Kelvin gives us units of Kelvin. So that's where the unit, Kelvin, comes from for the slope. Right? So if we start out with this, what I wrote in black, which is our slope, negative 3,478 Kelvin, is equal to the slope term of our equation, which is negative of the heat of vaporization over R. Since we've got a negative on both sides, we can multiply both sides by negative 1. That gets rid of that negative term. And so now we have 3,478 Kelvin equals the heat of vaporization, and the gas constant R is 8.314 joules per mole Kelvin. Okay, so since that is in the denominator, we have to multiply both sides by that, right? 8.314 joules per mole K divided by 8.314 joules per mole K, that becomes 1. But now we've got 8.314 joules per mole K times the 3,478 K. The Kelvin units cancel, and you get 28,916 joules per mole. right? If you do the complete math, that's going to be equal to the heat of vaporization. This is a chemistry problem. Both of these numbers have 4 significant figures, so when we multiply those numbers, we'll get a result with 4 significant figures. When we round to 4 significant figures, we get 28,290 joules per mole. Or if we divide that by 1,000, we get 28.92 kilojoules per mole. Right? So you should be able to look at a plot of data, or given data, create a plot, that is plotting 1 over temperature in 1 over Kelvin, the natural log of the pressure. What's nice about the Clausius-Clapeyron equation is the units of the pressure don't matter. It will change where the y-intercept is, and it will change the value of beta. But since beta is so specific for each substance, we're usually not interested in beta. So it doesn't affect the slope. So as long as all of our points are in the same pressure units, we can use the Clausius-Clapeyron equation and get the same result for the heat of vaporization. Okay, so here's another plot that we can evaluate, right? So a Clausius-Clapeyron equation is used to plot the natural log of the pressure. Note here it's in kilopascals versus the 1 over the temperature, right? We've got some points. There's a best fit line through it. And in the best fit line, it gives us an equation with a slope. Okay? So knowing that the Clausius-Clapeyron equation, the linear form is this, we can translate this theoretical equation into this, that the natural log of the pressure is equal to this value of the slope. The units of that slope are Kelvin, for the reason we showed you before. We've got our x variable was 1 over the temperature, and our y-intercept is 33.6. There are no units there because it's got to have the same units as the natural log of pressure here, and natural log numbers have no units. So there's no unit on this y-intercept value. So we start off with that slope, negative 9.31 times 10 to the third Kelvin equals negative of the heat of vaporization over R. We're going to multiply both sides by -1 to get rid of the negative on each side. And so then we end up with this, 9.31 times 10 to the third Kelvin is equal to the heat of vaporization. We've substituted in the value for R. Since we've got that in the denominator, we have to multiply both sides by that to get rid of that in the denominator. Right? That divided by that is 1. Right? On the left side, we've got a Kelvin unit in the numerator, a Kelvin unit in the denominator. Kelvin divided by Kelvin is 1, leaving only joules per mole. We multiply through 8.314 times 9.31 times 10 to the third. We get 77,403 joules per mole as being equal to the heat of vaporization. Because this number is only given in 3 significant figures, our answer must only have 3 significant figures. So if we round to 3 significant figures, we get 77,400 joules per mole. If we convert that to kilojoules, that is 1 kilojoule is 1,000 joules, you get 77.4 kilojoules per mole. So given that kind of data, you should be able to find the heat of vaporization for a given liquid from that kind of plot. Okay, so the linear form is one form of the Clausius-Clapeyron equation. What we find is that in some cases, especially in a general chemistry class, there are situations where it's convenient to use a 2-point form of the equation. So this slide shows how we go from the linear form to the 2-point form. And it will actually take 2 slides to get there, right? So we start off with our linear form of the equation, right? So we've got the natural log of the vapor pressure here, right? We've got our slope that we showed. We've got our x variable, 1 over the temperature, and we've got our y-intercept. So to create a 2-point equation, we're going to need 2 relationships. So we're going to have a temperature, right? We're going to have a temperature 1 and a vapor pressure 1 that goes along with it, and a temperature 2 and a vapor pressure 2 that goes along with it. So we're going to take this equation, and we're going to substitute temperature 1 and pressure 1 into this once, and we're going to substitute temperature 2 and pressure 2 into this. And what I didn't show is if you're going to write them side by side, and then you're going to subtract the 2 equations from each other. And so what I'm showing you is the result of that subtraction. So on the left side, right, we always, if we take the second case as our final, right, if we take that as the final, right, we always subtract initial from final. So it's always final minus initial, right? So that's why I go, right, the natural log of pressure 2 minus the natural log of pressure 1 on the left side, right? So we subtract those 2. And then that's going to give us, right? Actually, let's do it this way to keep it consistent, left and right. Right? So there was 1, right? So we're showing 2 minus 1. Okay, so on the right side, we'll take, have to remember to change colors. We'll take 2, right? The final case minus the initial case. Okay? So can we see that? Now, as we continue, right, we're going to keep the left side of our equation the same. We're not going to deal with that yet. But one of the things that we can do in this subtraction is group like terms. That is, we can multiply our -1 through here, right? So we can get, right, our heat of vaporization over R minus, our heat of vaporization over R times 1 over T2 minus our heat of vaporization over R times 1 over T1. Right? We can group those terms together. And we can group our natural logs of beta together. Right? This minus this. Right? So it's, let's see if I can highlight that better. Right? So we're going to take this minus this to give us this, and we're going to take this minus this to give us that. Right? So if you follow through the mathematical logic, you can see that. And now, right, if we go back here, since this term is the same in both of these terms, we can divide it, we can divide both terms by that and then multiply it out in front, so we can pull that term out in front and put our temperature terms together. Okay? So are we good with where we are at this point? So now we'll move on. We'll carry this equation over and we'll finish our manipulations. Okay? So that first equation here is the one we ended the last slide with. Right? So let's look at what we have to do to deal with this. Right? So one thing we can do is we can pull this negative term out front as -1. Right? And then we can multiply this -1 through this term. And note, natural log of beta minus natural log of beta is 0. So that takes itself out. So if we take the -1 through this term, then T2 becomes the negative term, right? 1 over the temperature 2 becomes the negative. And 1 over temperature 1, negative times negative, makes that the positive term. And also we have to remember our rule, that is that if we have the natural log, right? If we have the natural log of A minus the natural log of B, that is equal to the natural log of A divided by B. So we can apply that rule on this term. Right? We can apply that rule on this term, which gives us this. And so this is the final form of the most commonly presented form of the 2-point Clausius-Clapeyron equation. Right? So that's where we get that 2-point form. Now, one thing, if you struggle remembering the relationship, one thing that sometimes helps is to notice that, right, pressure 2 is first and temperature 2 is last. Right? Pressure 1 is second in the denominator. Temperature 1 is first. So the pressure, the 2's are on the extremes. The 1's are in the middle. And that heat of vaporization over R is the constant between them. Okay? That might help you remember the equation. Okay, so again, I've put the math down, but I want to talk through it. Okay, so bromotrifluoromethane has an equilibrium vapor pressure of 99.5 kilopascals at 215 Kelvin. So there's one pressure-temperature pair. And 570 kilopascals at 260 Kelvin. That's another pressure-temperature pair. Using the 2-point Clausius-Clapeyron equation, determine the heat of vaporization for this substance. Okay? And here's showing some conversions. But remember, because we've got a ratio of pressures here, whatever units we have for the pressure, divide out here. So that makes the Clausius-Clapeyron equation really flexible. Whatever pressures we start out using, that's the pressure that we can carry through, because it's always a ratio of pressures. Okay? I don't know why I left this out, but apparently when I was writing this down, I didn't finish it. So this is 1 over T1 minus 1 over T2. Remember, to get it straight, I used my relationship that if this is pressure 2 first, then temperature 2 is last. If pressure 1 is second, then temperature 1 is first in this term. Okay? So I take this equation and I substitute in the numbers from my problem. Right? I'm taking this as pressure 2 and temperature 2. So there's pressure 2, there's temperature 2, right? The 260 Kelvin. I'm taking this pair as pressure 1 and temperature 1. So there's pressure 1, there's temperature 1. The heat of vaporization is what we don't know. That's our variable. We know the value of the gas constant R is 8.314 joules per mole Kelvin. Right? And we try to carry units all the way through our equation because it always helps us out. Lets us know if we're doing our math correctly. Okay? So I'm going to take these two numbers and divide them. So 570 kilopascals divided by 99.5 kilopascals gives us 5.72864. There are only 3 significant figures here, but we always carry more significant figures so that we don't get rounding error in our significance place. We always carry more, round at the end. So we get this number, 1 over 215K, gives us 4.651 times 10 to the minus 3. Again, carrying more figures than are significant. 1 over 260K gives us 3.846 times 10 to the minus 3. 1 over K. Right? And we still got that term that we haven't touched. If we take the natural log of that number, we get 1.74548, again carrying extra terms. If we subtract these two, we get 8.05009 times 10 to the minus 4. Just as a note, right? Just as a note, right? These numbers, the temperatures, had 3 significant figures, which means that the decimals we make from them each have 3 significant figures. But when we do the subtraction, note that we're 10 to the minus 3 here, and we end up with 10 to the minus 4 here, which means this term, which is significant, is in this place and it disappears. So if you actually do a careful analysis of the significant figures of this problem, this number has 2 significant figures. And so we have to keep that in mind when we get to the end of our problem. Okay? So, at this point, we've reduced our numbers. Now we have to do some algebra to isolate our variables, right? So our variable we're trying to isolate is this one, right? So we have to multiply both sides by 8.314, right? That's going to move 8.314 to the right because that 8.314 on the left will cancel that. It'll divide out and be 1. We have to divide both sides by this number, which puts that number in the denominator over here. If we do the math, right, note we have a 1 over Kelvin unit here, which cancels the Kelvin unit there, and you just end up with joules per mole. So when we do the math, you get 1.8027 times 10 to the 4th joules per mole. Since we were doing math with a number that had 2 two significant figures in it. Our result will have two significant figures. So if we multiply that out, convert it to standard notation, you end up with 18,000 joules per mole. Converting that to kilojoules per mole gives us 18 kilojoules per mole as the heat of vaporization for the bromo-trifluoromethane given in this problem. Okay? So let's look at a different use of the two-point Clausius-Clapeyron equation. So in this one, we're using a substance called carbon disulfide. It has a vapor pressure of 4.68 kilopascals. It's also given in atmospheres. Again, because of the flexibility of the equation, we could work it in either pressure unit at minus 25 degrees Celsius. So there is a pressure-temperature pair. It has a heat of vaporization of 28.69 kilojoules per mole. And the question is, what would be the vapor pressure at a new temperature of plus 25 degrees Celsius? Well, we're given temperatures in degrees Celsius, and the first thing we have to remember is that we have to work, because the units of our gas constant are in Kelvin, and because of the proportionality that we have, our temperatures have to be in Kelvin. And so I just wanted to remind people what we're really doing when we convert Celsius to Kelvin. So when we say we are at minus 25 degrees Celsius, we are saying we are 25 degrees Celsius below the boiling point of water. So 1 Kelvin degree is equal to 1 Celsius degree, which means that tells us that we are 25 Kelvin degrees below the melting point of water. So we're 25 degrees below the melting point of water, right, as our reference temperature. There's 1 Kelvin degree per 1 Celsius degree. That means we're 25 Kelvin degrees below the melting point, the freezing point of water. And so if the freezing point of water is 273.15 Kelvin, that gives us this final temperature as our first temperature. If we're 25 degrees Celsius above the freezing point of water, there's 1 Kelvin degree for 1 Celsius degree. That means we are 25 Kelvin degrees above the freezing point of water. The freezing point of water on the Kelvin scale is 273.15. So we're 298.15 Kelvin is our final temperature, and we're going to use that as temperature 2. Right? So we have to make sure we keep those paired. So in the form of our equation, we don't know pressure 2, right? That's what we're trying to find. We do know pressure 1. We know the vapor pressure, but note the vapor pressure is given in kilojoules per mole, but the unit of the gas constant R is joules per mole Kelvin. So this unit has to match this unit, so we have to convert kilojoules to joules. So that's 28,690 joules per mole. We have 1 over our temperature 1, right? What we found here, the 248.15 Kelvin, minus 1 over temperature 2, the 298.15 Kelvin. So this is the equation that we're solving for this pressure 2. Okay? Now, one problem with this and one pitfall is students forget their rules for subtracting fractions. If you're going to subtract these as fractions, first you have to find a least common multiple, or at least a common multiple, for the denominator of each. You cannot subtract fractions that have different denominators. Now, if we remember back to grade school when we did that, sometimes finding those common denominators can be a great challenge. Now, given that these are numbers with significant figures, one of the things we can do is convert these fractional numbers to decimal numbers, and then we can subtract the decimals. But we can't just directly subtract these numbers. That's violating, logical rules of mathematics. So what I've done is I've taken this number, divided it to get this decimal, and this number and divided it to get this decimal, so that I don't have to deal with the common denominator problem. Okay? So I'm going to take this fraction, right? I'm going to take this fraction and divide it and get this number, right? I'm going to take this fraction and divide it and get this number, and this fraction and divide it and get this number. Okay? So if you're following along, you should make sure that you get something similar to those numbers. And note the units, right? If we note here, joules per mole, and joules per mole gives you 1, leaving only a Kelvin unit in the denominator here, and that gives us Kelvin, right? 1 divided by 1 over Kelvin gives you Kelvin as the units of the slope. That's what we've gotten consistently. And each of these numbers in this fractional term have Kelvin in the denominator, right? 1 over Kelvin. So each of these numbers would have units of 1 over Kelvin, which remember is appropriate because you can't add or subtract numbers unless both numbers have exactly the same units, right? So one of the things you can always check if you're following your units, whenever you're doing an addition or a subtraction, check and make sure that those two numbers have exactly the same units, okay? So when we do the subtraction, right? When we do the subtraction in this term, we're going to get this number, right? 6.758 times 10 to the minus 4. Okay? And again, if we're following through our significant figures, our temperatures were actually given to 2 significant figures. But in the addition, we gained a significant figure in the addition. So these numbers actually have 3 significant figures. So our decimals after our division have 3 significant figures. But again, our subtraction costs us the significant figure here, right? Because we get a number that is less than that. And so this number actually has 2 significant figures if we are following through and being specific, okay? So it has 2 significant figures. Okay, so now we're down to this equation, right? We still haven't done anything with our left side. Our left side is exactly as we started it, right? But now that is equal to 2.332. And because we have Kelvin times 1 over Kelvin, this number has no units, right? Our units canceled, which is appropriate because natural log numbers are unitless, right? And we can see here we have a pressure divided by a pressure. Those pressure units would cancel, so we would have no units here, and it's appropriate that we would have no units there. Okay? So again, let's carry this equation to the next page. Okay, so there's the equation that we just finished with, right? With our variable inside the natural log term, right? That's difficult to deal with, but we can deal with it this way using this log rule, that the natural log of a divided by b is equal to the natural log of a minus the natural log of b. So we can take this term and separate it, right? So we have, right, we have this term, we get that term, and since this term is in the denominator, then we're going to subtract this term. Okay, so now we have the natural log of our pressure 2 minus the natural log of a number is equal to this number we found on the previous page. Right? So now we can evaluate that natural log and get a number. Right? So now we have that the natural log of our second pressure minus this number we just found as the natural log of this is equal to this number, 2.332. Since this is subtracted from this side, we're going to add it to both sides. And so we see that number added to the right side. Right? And so if we take this plus this, 2.332 plus the 1.435, we get this. And so we get an expression that says that the natural log of our second pressure is equal to this number. So we have a natural log equaling a number, right? And so if we remember our log rules, if the natural log of a number equals another number, then that means e raised to that second number is equal to the first number, right? So that means our pressure 2, right? Our pressure 2, right? Right? If we have the natural log of x equals y, right? Then our pressure 2 becomes our x number, and this becomes our y number, right? So that means that our pressure 2 is equal to e raised to that power, and if we put that in our calculator and evaluate it, you get 48.2 as the answer. And since our original pressure was in kilopascals and these were a ratio, right? If one pressure was in kilopascals, then the other pressure also had to be in kilopascals. And so that's why our answer then comes out as 48.2 kilopascals. If we want to evaluate it, we said that this whole thing would really have two significant figures. So that would be 48 kilopascals would probably be the best reported number as our vapor pressure at the second temperature. Okay? Now, we've got one more variation I want to talk about. Okay, so again, we're going to deal with carbon disulfide, and our given information at minus 25 degrees is the same, right? So, and our vapor pressure is the same. So we're starting with that same pressure. Now, the question asks, or it asks a different question. That is, what would be the normal boiling point of carbon disulfide? And it looks like they haven't given us a second temperature and pressure. So it looks like we've got too many variables. But what we have to remember is the definition of normal boiling point. Normal boiling point has a specific definition. The normal boiling point, right? The normal boiling point, okay, the normal boiling point is a temperature, right? So you have to say it is a temperature at which the equilibrium vapor pressure of the liquid equals the normal atmospheric pressure applied on the liquid. Remember that a liquid will boil when the applied pressure on the liquid is equal to the vapor pressure of the liquid. So there are two ways to make a liquid boil. One is to keep raising the temperature of that liquid until the vapor pressure equals the atmospheric pressure. That will make a liquid boil. The second way to make a liquid boil is to reduce the pressure on the liquid until the pressure gets down to equal the vapor pressure, then the liquid will boil, right? But at the normal boiling point, we're talking about 1 atmosphere pressure, normal atmospheric pressure. So at the normal boiling point, the vapor pressure is equal to 1 atmosphere. That gives us our second pressure, right? So since the definition of normal boiling point uses atmospheric pressure, I put 1 atmosphere as pressure 2, which means I went up here and I used the atmospheric pressure, right? The atmosphere measure of the pressure at temperature 1, right? So the temperature 1 then becomes the 248 Kelvin, that is equivalent to the minus 25 degrees Celsius. And we don't know temperature 2, the temperature that corresponds to the 1 atmosphere. So this temperature 2 becomes the normal boiling point. Again, because our gas constant R is in joules, we have to convert our heat of vaporization from kilojoules to joules. Okay? So, we can evaluate this fraction. All right, and we're going to take this 1 atmosphere as exact, right? This is not going to limit our significant figures. This is a measured number, so this is going to limit our significant figures. But again, we will carry more significant figures through our calculation, right? So, right here we have 1 atmosphere divided by 4.619 times 10 to the minus 2. That gives us this 24.65 approximately. If we divide this fraction, we get this number again. Joules per mole cancel. We have 1 over Kelvin in the denominator. When we do the division, that moves Kelvin to the numerator. We get that number. 1 over 248.15 gives us this number again, minus 1 over temperature 2. Okay? Now, if we take the natural log of this number, the 24.65, we get this number 3.075, right? Again, carrying more figures than are significant through the calculation so that we don't contribute to extra rounding error. So we will start the next slide with this equation. Okay, so here's this same equation that we had on the previous slide, right? And so we have to isolate our variable algebraically, right? And complicated by the fact that our variable is in the denominator of its term, right? So first, right, we will divide both sides of our equation by that term, right? So when we divide by that term, right, that term becomes 1 on the right side, but we have, on the left side, we have this number, which was a log number, so it has no units, divided by the number that was our slope. That's going to give us this number in units of 1 over Kelvin, right? Now we have this number in units of 1 over Kelvin. To isolate our variable, we have to subtract this from both sides of the equation. When we subtract it on the right, it becomes 0. When we subtract it on the left, we have two numbers, I neglected my units, but note here this is also 1 over Kelvin. So we are in the situation where we are subtracting 2 units with exactly this, or 2 numbers with exactly the same units. That's allowable. Since this one is bigger than this, note this is 10 to the minus 3, we get a negative number here is equal to, right, this number was negative because it was subtracted here, right? So if we multiply, since temperature 2 is in the denominator, we have to remember our algebra rules. We have to multiply both sides by temperature 2. That's going to, right, temperature 2 divided by temperature 2 is 1, right? And we want to get this term out of the way to isolate temperature 2. So we're going to divide both sides of the equation by that number. And so that divided by that becomes 1. That isolates temperature 2 on the left, right? We've got the -1 here divided by this term on the right. When we do that division, you get 318.6 Kelvin. If we go back and look, something reasonable is 3 significant figures. Actually, it's probably more like 2, but we're going to get something in the range of 319 Kelvin. Okay, so I hope this video has helped you see the ways we can use the Clausius-Clapeyron equation and how we can use the different forms of the equation and the different ways that we can approach solving for the different variables, especially in the 2-point Clausius-Clapeyron equation. Thank you. I hope this was helpful.